Chapter 5, Helmholtz energy and Gibbs energy. Section 5.6, Changes of U, H, A, G, S when ideal gases mix. The isobaric mixing of two or more ideal gases at the same temperature is equivalent to the expansion of the individual ideal gases. This is just because the mixing does not affect the potential energy or kinetic energy of any of those mixing gases. It only changes the volume of those gases. For example, let's look at this diagram. We're going to mix A and B. Now you can see A initially occupy a smaller volume. After expansion, A occupies a larger volume. Same for B. So really the volume of A is doubled, the volume of B is doubled. It's isothermal expansion. In an isothermal expansion, well, we know PV equals nRT. So when the volume of A is doubled, the partial pressure of A is halved. Same for the partial pressure of B. And this isobaric actually means what? It means the total system pressure is unchanged. So for example, over here, let's say initially PA is 1 bar, PB is 1 bar. After mixing, the system pressure is PA plus PB. Although both PA and PB are halved, the total pressure is equivalent to the initial pressure of A and also to the initial pressure of B. In that sense, we say this is isobaric mixing. However, remember, the partial pressure of A and the partial pressure of B are reduced in the mixing process. It's just the total system pressure remains unchanged. And also, if you look at the total volume of the system also remains unchanged. And the temperature remains unchanged. So really, P, V, and T of the system remain unchanged during mixing. Now what about U, H, A, G, and entropy? We'll analyze those. When A and B ideal gases are mixed, gas A and gas B do not really fill each other. This is because ideal gas particles do not attract or repel each other. Therefore, we have delta U equals 0. So there's no change in potential energy. And also, since it's isothermal, there's no change in the average kinetic energy. And because there's no change in the number of particles, we can say there's no change in kinetic energy. Therefore, delta U is 0. Delta H is also 0 because H is U plus PV. And delta U is 0. We have proven this. Delta PV is delta nRT, so delta nRT is 0. Again, it may be a little confusing. When we say PVT, we are referring to the entire system. So if this is 1 bar, this is 1 bar, we say the whole system has a 1 bar pressure. After mixing, it's still 1 bar. And we consider this the total volume of A and B before mixing as the volume of the system. And over here, this is the volume of the system, so there's no change in V. And finally, there's no change in T. So let's say we start from room temperature here, and finally we have room temperature. Again, P is the total pressure of the system. Over here, this P. The pressure of the entire system is equivalent to the initial pressure of A and initial pressure of B. And again, V denotes the total volume of the entire system, so this whole thing. The Gibbs energy of gas A decreases after mixing. Alright, why is that? It's because the Gibbs energy of A depends on the partial pressure of A. So we can use this equation. Delta G of A is the integral of V of A dP of A, and V of A is nART over PA, and we integrate this. We're going to get nART, the number of moles of A times RT, times the logarithm of PA final, divided by PA initial. And PA initial is the total pressure P. Alright, so we have this equation here. And what's this? What's PA final over P? That's simply the mole fraction of A after mixing. That's why we have this equation. Delta G of A, the change of the Gibbs energy of A, is N sub A times RT times the natural logarithm of the mole fraction of A in the mixed system. Similarly, delta G of B is equal to MBRT times the natural logarithm of X of B. X of B is the mole fraction of B. Alright, after the mixing, you have the mole fraction of B less than 1. Because Gibbs energy is additive, we can just sum up the change of the Gibbs energy of A and the change of the Gibbs energy of B to get the total change of the Gibbs energy of the entire system. We get this equation. Alright, we have RT and then times NA ln XA plus NB times ln XB. Somehow you realize this NA is just N times XA and NB is just N times XB if we use N to denote the total number of moles. Again, when we have the isobaric mixing of two ideal gases at the same temperature, there is no change in PVT, there's no change in U, there's no change in H. However, the Gibbs energy decreases. We have this two equation because after mixing, X sub A is less than 1, X sub B is less than 1. Therefore, delta G of A is negative, delta G of B is also negative, and we can sum it up. We get this. And we set N as the total number of moles of all gases. In this case, we have only two gases. It's just Na plus Nb. Na is N times Xa, Nb is N times Xb. Delta G is simply nRT times Xa ln Xa plus Xb times ln Xb. What if we have three ideal gases? We just need one more term. We need X of C times the natural logarithm of X of C. So we have the sum of three terms. We have delta G is equal to the sum of the Gibbs energy changes of A and B and C. What if we have N different ideal gases? Well, we'll have to resort to this uppercase Greek letter sigma. Sigma denotes the sum, and over here it's the sum of X of I times the natural logarithm of X of I. I is just the index of the ideal gases. I is from 1 to N. Alright? Again, there's no change in PV. Delta PV is 0. So delta A is equal to delta G. Why? A is G minus PV. So delta A is delta G minus delta PV. Delta PV is simply 0. And therefore, we have delta A is also equal to nRT times the sum of Xi ln Xi. The isobaric mixing of N different ideal gases at the same temperature results in no change in U and H. However, the Gibbs energy and the Helmholtz energy both decrease, and the change of A and the change of G are both negative. The equations are here. We can compute delta G using this equation, delta A using the same equation. And because delta U is 0 and we have delta U is delta A plus delta TS, somehow we can compute delta TS. Again, it's just because of this equation and temperature is constant, so we have this. And now we can just plug in the values. Delta U is 0, so delta A plus T delta S is 0. And delta A is this nRT times the sum of xi ln xi. So over here, this is delta A plus T delta S is 0. Using this equation, we obtain the expression of the entropy of mixing. It's negative nR times the sigma, or the sum of xi ln xi. This whole thing is greater than 0 despite the appearance of a negative sign. Only because every single term here is negative. The mole fraction of any species is less than 1. The logarithm of the mole fraction is negative. Therefore, the entropy change is positive. The entropy change of the mixing of ideal gases is always positive. Let's look at one example. Let's mix 3 gases, 0.2 moles of A, 0.3 moles of B, 0.5 moles of C, and then we mix them at constant pressure, constant temperature. The total number of moles is 1 mole, and delta S is simply, we're going to use this equation, negative nR, and then we have the sum of 0.2 ln 0.2, 0.3 ln 0.3, 0.5 ln 0.5. Do all the calculation, we get 8.56 joule per Kelvin. This is the mixing entropy, for this process of mixing 0.2 moles of A, 0.3 moles of B, 0.5 moles of C. Again, the entropy always increases when we mix ideal gases or even real gases. In general, the mixing of different gases always results in a significant increase of entropy.